Hello, welcome to Arcteq second webinar Wednesday. What you see here is a recording, but I will be answering to your questions on live chat. The topic of the day is Earthfall in distribution networks. My name is Jani Vainionpää and my title is Application Engineer. The primary purpose of grounding electrical systems is to provide protection against electrical faults. However, this was not realized until the late 1970s. Until then, most commercial and industrial systems were ungrounded. Although ungrounded systems do not cause significant damage during the first ground fault, the numerous disadvantages associated with the ground faults resulted in a change to the grounding philosophy. There are other advantages for a grounded system, such as reduction of shock hazards and protection against lightning. Ground fault current at the fault location is decreased by galvanically dividing the network into smaller parts by using multiple incoming power transformers. More likely used method today is to compensate the capacitive fault current by using a grounding inductance at the incoming power transformer star point. But notice that compensation can also be separated from the transformer star. Overvoltages caused by a voltage neutral point dislocation are aging insulations of the network. Also, fault current has a heating effect and it causes a fire hazard. Weaker insulation during ground fault may evolve into a three-phase short circuit. Research results are indicating that 98% of all faults are ground faults. A leading initiators of ground faults is a exposure to moisture and dust and shorting by a tool or rodent or another animal. In solidly grounded networks, the transformer star point is directly grounded. Fault current in single phase to ground fault is as great as in two-phase short circuits. Therefore, protection against earth fault can be done by simply using overcurrent protection. Fault current in healthy feeders is close to nothing when compared to the faulty feeder. A resistance grounded network operates very similar to directly or solidly grounded network. The only difference is that the fault current is limited or restricted by using an external resistance. This resistance is connected directly to the star of the transformer. In ungrounded network, a faulty phase touching the ground directly or through resistance has no passage to circulate to the star point of the transformer. In direct phase to ground fault, the voltage of the network changes dramatically. The voltage of the faulty phase may drop to almost non-existing, and the remaining two healthy phases can increase up to line-to-line voltage level. This means that the healthy phase voltage can increase square root 3 times larger than in normal circumstances. This condition is bad for the network insulation, and in case the phenomenon lasts long enough, there is a possibility that the condition evolves into a three-phase short circuit. The fault current in isolated networks comes mainly from the system capacitances, meaning that the amount of cables and overhead lines in total affects directly to the capacitive fault current size at the fault location. In upper example, the fault current at the fault location is roughly 20 amps of capacitive current. But what the relay 1 sees at the beginning of the line is only 18 amps. These 18 amps are the capacitive current of healthy feeders, which are circulating through the transformer star point and to the fault location. Feeder A current also circulates through the transformer star point and back to the fault location, but relay 1 is unable to see this because it moves to both directions at the measurement point. Therefore, the fault current of faulty feeder relay number 1 is 18 amps towards capacitive plus 90 degrees. The healthy feeders only see their own capacitive current which is flowing towards the transformer star point. It means that relay number 2 sees 8 amps capacitive current flowing to reverse direction. Since the tripping area is on capacitive side, the relay number 2 is not going to perform a trip. The second faulty situation below, it can be noticed that when the fault is in feeder D, the relay number 2 measures 12 amps of capacitive current flowing towards the fault and will trip the faulty part of the network. Relay 1 sees only 2 amps of capacitive current flowing to reverse direction and does nothing. Reactance grounded network, which is also called compensated network. When underground cabling increases by either having extremely long lines and/or by having many outgoing feeders, the total capacitance may increase to several hundreds of amperes. Such a large current at the fault location can be dangerous and is therefore limited by using compensation coil at the star point of the transformer. The coil can be tuned to slightly under or overcompensated, but it is quite normal to tune the coil into a way that the current at the fault location is close to nothing. Since the fault current at the fault location decreases to non-existing level, it is quite impossible to perform a selective tripping of the fault at the beginning of the feeders. Due to this, an external parallel resistance is used next to the compensation coil at the star point of the transformer. In our example, the network is slightly undercompensated and 17 amps inductance is used in 20 amp network. This means that the fault current at the fault location is roughly 3 amps of capacitive current. When the resistance, which in this case is also 3 amps, is connected, the fault current at the fault location increases to 4.24 amps, and the direction is roughly 45 degrees. But what does the relay measure? In the first example picture, the relay number 1 sees the healthy feeders combined capacitive current, which in this case equals 18 amps, minus the compensation coil effect, which is 17 amps. The total capacitive current of the relay 1 is only 1 amp to direction 90 degrees when the resistance is not connected. But when the resistance is switched on, the 3 amp resistive current flows in the system towards the fault location. When this 3 amp resistive current is added to the 1 amp capacitive current that the relay 1 measures, the total current what the relay 1 sees is 3.16 amps. Relay number 2 measures 8 amperes flowing to reverse direction and will not trip. In the below case, the relay number 1 sees 2 amps of capacitive current flowing to reverse direction, but the relay number 2 measures something different now. The total capacitive current of healthy feeders is only 12 amps and the compensation coil is 17 amps. It means that there is no capacitive current at the beginning of feeder D, but inductive current, and the amplitude is 5 amperes. So basically the faulty feeder is pointing to healthy direction. But when the parallel resistance is connected, the relay falls to resistive side and the tripping can be performed correctly and selectively. The increase of medium voltage cabling, connection of distributed generation and compensated networks, along with distributed compensation has led to new challenges in earthfall protection of distribution feeders. Challenging combination of short cable feeders, long overhead feeders, and mixed cable and overhead networks is increasing significantly among distribution system operators. Relying on conventional protection method may lead to nuisance strips of healthy feeders or undetected faults in faulty feeders. When protecting compensated long-distance cables and overhead lines, it is in some cases difficult to distinguish between healthy and faulty feeders when protection is based on merely measuring the angle and magnitude of residual voltage and currents. Earthfall protection often requires information on network status, whether it's ungrounded or compensated. When changing between these two statuses, setting groups must be changed, and especially in case of distributed compensation, the change may be difficult or impossible to arrange. Solution for this, Arcteq provides new broad range mode available in AQ200 series protection and control IEDs can protect against earth fault in both ungrounded and compensated networks without setting changes. The algorithm reliability is further increased using a new multi-criteria detection. This optional additional tripping condition for compensated networks uses Arcteq's patented high-resolution intermittent earth fault algorithm with added symmetrical component calculations of phase, currents, and voltages. Multi-criteria algorithm can be tested with Comtrade files supplied by Arcteq. Function requires connection of three phase currents, residual current, and zero sequence voltage to operate correctly. To avoid unnecessary trips due to CT errors, encroachment area in compensated long healthy feeders can be added. For a complete coverage of feeder earth faults in compensated networks, the intermittent or transient type of earth faults are to be protected by Arcteq's patented intermittent earth fault protection stage available in AQ200 series feeder protection. For a complete coverage of feeder earth faults in compensated networks, the intermittent transient type of earth faults are to be protected by Arcteq's patented intermittent earth fault protection stage available in the AQ200 series feeder protection IEDs. The problem that can arise in unsymmetrical cable and overhead lines at the station is to recognize the difference between healthy and faulty feeders. In this tricky example, we've got outgoing feeders, and while the longest feeder is 65 kilometers long, the shortest one is only 2 kilometers. The total capacitive current of the network is 135 amperes, and the used compensation coil reduces the total capacitive current at the fault location by 128 amperes. Parallel resistance size is only 2 amps. And we are here in discussion today that the use of external resistance should be avoided in the future. So the protection of unbalanced compensated network becomes even more challenging. Let's focus on feeder D. In case this line is healthy and the fault is located either on feeder A, B, or C, the capacitive healthy current of feeder D is 180 amps, which is flowing to reverse direction. Already this can cause a problem. Notice that the resistive setting is no more than 1 amp. At the beginning of feeder D, even a minor error when measuring the earthfall current can tilt the vector towards the tripping area. This would cause the healthy feeder to trip. To avoid nuisance tripping, an encroachment area for CT inaccuracy should be implemented. This encroachment area should only be used on the tricky long feeders which are giving us all the trouble. But when the earthfall happens on feeder D, the situation is not much better. The capacitive current of remaining few healthy feeders is only 15 amps, and the compensation coil is adjusted to 128 amps. It means that the fault current is 130 amps towards inductive minus 90 degrees angle plus the parallel resistance effect of roughly 1 amp. As you can see, it is impossible to perform the tripping correctly. Therefore, the new SCC tripping method that was represented on previous page should be used with this line. The SCC method performs the trip based on the change in the network at the very beginning of the fault. To analyze the change, all three phase currents along with the residual current and the zero sequence voltage must be connected to the relay to be measured. Power cables are manufactured in factories under controlled environment and sophisticated online monitoring. The completed cables are further tested according to standard testing guidelines before acceptance for use. However, the cables laid at the site may not deliver the required performance due to adverse installation conditions and unintentional damage during cable laying. Jointing is required to be done at site of installation where the trench is often infested with dust, moisture, and vibrations. These unavoidable factors can be detrimental for the high-tension cable joint, which requires a clean environment for manufacture. Human factors can also present in jointing as the job is done manually. Though joints are always done by trained and experienced jointers of sufficient reliability, human error can creep in, which is unavoidable. Furthermore, a joint is a weakest part of an ungrounded cable system owing to the three types of stresses which are predominant in joints. These are the thermal stress, electrical stress, and mechanical stress. When isolation of cable end is failing, it starts to leak current to the ground. Restricted earthfall function is used for residual differential current measurement for transformers, and this same method can be used for cable end differential functionality. Operating principle is low impedance differential protection with settable bias characteristics where differential current is calculated in between of summed phase currents and selected residual current input. In CED mode, the function provides natural measurement unbalance compensation in order to have higher operating sensitivity for monitoring cable end faults. You can have a closer look for this topic in the future upcoming webinar Wednesday. In high-tension cables, the voltage stress appearing across cable insulation is considerably high. Every precaution is taken in cable factories so that the polymeric insulation is free from voids, impurities, semiconductor protrusions, and so on. However, in real life, it is not possible to design a 100% void and impurity-free cable insulation. The voids and impurities are a region of localized discharge and heating which ultimately develops into a carbonized bath in insulation. Formation of carbonized pocket cause the effective insulation thickness to reduce and develop a carbonized conducting tracking bath, which ultimately results in a dielectric breakdown. Polymeric insulations are hygroscopic to some extent. The seepage of moisture through the cable sheet can percolate through the insulation. The water molecules get charged as the conductor acts as cathode and the screen as anode. The charged water molecules travel through the insulation from the earth screen towards the live conductor via insulation by a process called electrophoresis. Water causes conducting path through the insulation, resulting in dielectric failure in a long run. Unlike electrical drilling, water drilling is a slow process which develops over a long period of time. The intermittent earth fault protection shall be coordinated with busbar residual voltage protection in such a way that in case of intermittent earth fault, the faulty feeder will be in all cases stripped by intermittent earth fault protection function prior to the residual voltage protection function, considering a sufficient safety margin as well. On the other hand, since an intermittent earth fault causes significant network stress, the protection trip should be performed as fast as possible. The strike-through time of an intermittent earth fault in closed resonance-tuned network sets the limit for the minimum operate time of an intermittent earth fault protection stage. To ensure a correct protection operation in all cases, the reset time of an intermittent earth fault stage shall be set according to the network in question. The size of the network is dominant factor in defining the strike-through time interval. In larger networks in amperes or in larger network in amperes, a less frequent strike-through can be expected. The following can be presented as a rule of thumb in small or medium-sized networks less than 60 amps, approximately 250 to 350 millisecond strike-through interval, and in large network, roughly 100 amps or more, approximately a 500 millisecond strike-through interval is expected. As a recommended practice, it can be stated that the reset time of an intermittent earth fault stage should not be set lower than 450 milliseconds to obtain a network-independent setting. Using this reset value, one can be sure that function will not reset too early in resonance-tuned network. The intermittent earth fault protection shall be coordinated with busbar residual voltage protection in such a way that in case of intermittent earth fault, the faulty feeder will be in all cases stripped by intermittent earth fault protection function prior to the residual voltage protection function, considering a sufficient safety margin as well. On the other hand, since an intermittent earth fault causes significant network stress, the protection trip should be performed as fast as possible. The strike-through time of an intermittent earth fault in closed resonance-tuned network sets the limit for the minimum operate time of an intermittent earth fault protection stage. The size of the network is dominant factor in defining the strike-through time interval. In larger networks in amperes or in larger network in amperes, a less frequent strike-through can be expected. The following can be presented as a rule of thumb in small or medium-sized networks less than 60 amps, approximately 250 to 350 millisecond strike-through interval, and in large network, roughly 100 amps or more, approximately a 500 millisecond strike-through interval is expected. As a recommended practice, it can be stated that the reset time of an intermittent earth fault stage should not be set lower than 450 milliseconds to obtain a network-independent setting. Using this reset value, one can be sure that function will not reset too early in resonance-tuned network. Typically, the maximum operate time of the intermittent earth fault function is dictated by busbar residual voltage protection. If the residual voltage protection is set to very fast tripping, it may be necessary to prolong the set value of the same. As a recommended practice, it can be stated that the operation time of an intermittent earth fault stage should be 500 milliseconds, counting from the first strike-through. In this case, the protection tripping requires minimum 2 strike-throughs, even in resonance-tuned networks where strike-throughs happen less frequently. If the residual voltage protection is set to very fast tripping, it may be necessary to verify the reset value of the residual voltage protection. In no case shall the residual voltage protection time be faster than set intermittent earth fault operate time plus circuit breaker operate time added with reset time of residual protection or residual voltage protection stage. If an intermittent earth fault protection start is used to block regular non-intermittent direction earth fault protection, the blocking should be applied for both healthy and faulty feeder relays. In general, if intermittent airfall protection is not used to block directional airfall protection, it shall be verified that the operate time of regular directional airfall protection is longer than said intermittent airfall protection operate time. It is recommended to block regular directional airfall protection only to avoid start event of directional airfall protection during intermittent airfalls. Or, if directional non-intermittent airfall protection is set to faster operate time than intermittent airfall protection itself. Lastly, by using Arcteq relays, it is possible to build an individual auto-reclosing scheme for airfall protection. A correctly timed shot can be set to protect overhead lines against intermittent airfalls in compensated networks. While auto-reclosing won't be performed for underground cables, it is recommended to use one shot for overhead lines. Therefore, real faults can be recognized efficiently and network operates more reliably.
And this is the end of our second Arcteq webinar Wednesday. I thank you all for participating. We will be available for a while in chat in case any questions came up to your mind. Our next webinar Wednesday will take place next week. The topic is IEC 61850 training and programming. Thank you.